Hello, good morning to you all. So in the last few classes, we looked at the design aspect of distributed database system. More specifically, we have seen that how one can do the fragmentation of global schema or global relations horizontally as well as vertically. And we have seen after that, we have seen that how these fragments can be allocated using different allocation strategies. So this is typically the design aspect of distributed database system. And if you look at the flow, so there is a problem description. Then we are looking for generation of global schema that is using some data models. Then we are applying the database design, advanced database design. Typically, we are talking about the normalization, and then doing the fragmentation, then allocation, that is allocating the fragments to the site. And after that, we are looking at the physical design. So these are all the steps involved in the design of distributed database system. Okay, that is the one aspect of it. Now let us move on to the another part of the distributed database system, that is distributed database management system. We are all studied database management system. So this is an engine or a bundle of software which is responsible for manipulating the data as well as responsible for integrity, maintenance of the data, and so on. Now, those aspects are same in the case of distributed database management system. In addition to this, it has to perform two main things. One is the transparency. So we have seen that what are the different kinds of transparency, and another one is that one is the transparency, and another important thing is that it has to do the another thing is that it has to do the handling of different kinds of queries. We know the local queries, remote queries, and the global queries. So whenever there is a global queries, you should know that how the global queries can be decomposed and the result is going to be integrated. Okay. Now we are moving on to the query processing aspect of distributed database management system. So that is the main engine part of the DBMS. So before starting with that, let me go through the introduction to the query processing. And as per this session is concerned, I'm just talking about introduction to the query processing. And the next session onwards, I'm going to talk about how exactly the query processing is going to be done in a distributed environment. That is distributed query processing. Okay. Now, you know that there are two kinds of query languages. That's what you have studied in the centralized database management system. One is non-procedural query languages and procedural query languages. Let us look at these two things in a detailed manner. Let me start looking at the non-procedural query languages. Okay, and with reference to the database system, non-procedural query languages are typically the relational calculus. Why it is called non-relational? Because the whole idea here is that one need to specify what exactly the user wants, but not how to get it. Okay, that is very a declarative way of specifying the requirement. So that's what is going to be done in the relational calculus. And the examples are SQL, QBR are example for this. For example, if you want to suppose you are having an employee table, if you want to retrieve the salary which is greater than say 1 lakh, then the query is simple: select star from employee where salary is greater than 1 lakh, and that means we are declaratively specifying that what we want, and we are not specifying at this point that how to get it. Okay, that is a non-procedural languages. And relational calculus is an example for that. There are two types. Okay, one is the tuple relational calculus, and other one is the domain relational calculus. Tuple relational calculus, here the relational expression is of the form t such that tau of t, where t is a variable which is ranges over the tuple. That means it's usually we are always referring to the minimal element in this case is going to be tuple, and tau of t is a condition. So we are going to retrieve all the tuple which satisfies this condition, right? So that is a tuple relational calculus. And I'll give an example here. And this example shows that we want to retrieve the names of all employees, okay, such that this condition is true. What is the condition? Employee of t. That means retrieve all the tuple from employee, and for every tuple you just look at the salary, that's employee of t dot salary, which is greater than 1 lakh, and you just retrieve the names of all the employees. And what to note here is that the variables are range over the tuples. That's what we are showing here. Okay, so this is an example for this. And SQL is based on the tuple relational calculus. And if you look at the SQL, so the variables which we are going to specify is the reference to the tuple. That is a tuple relational calculus. And coming to the domain relational calculus, the expression is of the form a1 into etc. up to n with the tau of these attributes. Sorry, tau of these variables. But here these variables are range over the attributes. Suppose the relation is having 5 attributes, so I'm going to have A, B, C, D, E, 5 attributes specified here, and each attributes are corresponding to the attribute in the table. Okay, so each variable is corresponding to the attribute in the table. And I'll give an example. So that is this example retrieves the E names where the salary of the employee is greater than 1 lakh. So here I'm assuming that I'm having X E number is one variable. It may be ABCD, there's no problem. X, I just put X underscore E number, X underscore E name, X underscore salary. These are the three variables corresponding to three attributes, only three attributes in the employee table. Okay, so I'm retrieving X underscore name because here the variables are range over the attributes. Okay, and so this is the table, and X salary is greater than 1 lakh. So we are going to check this variable. So this variable is going to assign the values of attributes salary, right? Greater than 1 lakh. So that's expression, relation calculus expression for this. And example for this domain relation calculus is query by example. I think you have seen this. We have seen this in the centralized database system where typically we are following the table filling approach in the query by example. So this is a non-procedural. Coming to the procedural one, relation algebra is an example for procedural one in the database DBMS environment. Here it's a procedural because you are going to specify how you are going to get the result. It's having a set of operations, right? And binary operations are intersection, union, difference, addition, product, join. Okay, there are different types of joins. There is equi-join, semi-join, equi-join, theta-join, natural join. There are all different kind of binary operation, right? And there are different kind of join operation. And binary operations are the select and project because they are operating only on single relation. These are all operating on two relations, right? So here, this is typically the procedural one is typically descriptive type because here we are talking about how to evaluate the queries. Right? So this is the procedural one. So we have seen non-procedural one and the procedural one. Non-procedural one, relational calculus, and procedural one, relational algebra. Okay, the expression based on relational algebra. Let us move further. Now, when it comes to the query process, so the user query is a non-procedural. So this is the flow of execution. The query is specified in a non-procedural way. That is SQL or QB is an example for that. And internally, DBMS is going to convert into a procedural query. That is the expression using the relational algebraic operations. And then it is going to optimize those queries. And then it is going to do the execution with reference to the database. So this is typically the block schematic of query process. Let us look at this optimization in a centralized database system in a very basic way. So some of the basic optimization steps are shown here. So you know that suppose I'm having cascaded a select command. I've shown here only two: select condition 1 and then select condition 2 on R. It is what it means is that first I have to apply this condition 2 on relation, and you know all the relation algebraic expressions is giving back to the relation, that is table, right? Now this you are again applying this condition, that is condition 1 to that table. So the table is going to be accessed twice, and it's a costly affair. What is optimization? You put this condition together. So how you can put it? Select condition 1 and condition 2 on the relation. So I'm going to access the relation only once. That's how the optimization is going to be. Optimization is achieved. Similarly, with reference to the project operation, suppose I have cascaded project operation. Say in this case, I have shown two such cascading. The project of attribute list 1, project of attribute list 2 on relation R. This is simply equal to the project of attribute list 1 on R. Of course, this is possible to execute provided attribute list 1 is the subset of attribute list 2. So if you're having this cascaded one, then you simply take the outermost project operation. So that is the result, and hence you are going to optimize this kind of cascaded projects. Coming to the select and the project, select and the join operation. Suppose I have select on some condition F or join S. This can be optimized as applying the select condition only on F and then join with S. Okay, provided F is having the attributes, F is a condition, it is having the attribute pertaining to F only, R only. Right? How it is going to be optimized? Because here we are going to reduce the number of tuples, because select operation is going to reduce the tuple. So you are going to reduce the number of tuples, and hence you are going to reduce the number of operations. Okay. So this continuing further, it is equal to R join select of F on S if F is pertaining to S, or it may be written as select of F1 on R join select of F2 on S. If F pertaining to both R and S, what it means is that say F is equal to F1 and F2, where F1 is pertaining to R and F2 is pertaining to S. Okay. In such cases, you can have the optimization expression of this kind, where the point here is that I can perform this operations, this operation and this operations on parallel, and do the operation after that. Okay. And other one is that select of F3 or select of F1 R join select of F2 S, where the expression is of the form F is equal to F1 and F2 and F3, where F1 pertaining to R, F2 pertaining to S, and F3 pertaining to both R and S. In such case, I can just pull out F3 at the outermost level and perform and apply F1 the select operation on F1 on R and select operation on F2 on S. Okay, that's optimization. So continuing further, so select operation with reference to the binary operation, that is union. So here this is equal to select on F, select F on R, union select F on S. You know that all these operations are possible because the union, intersection, and the difference are having the union compatibility. That's why I can apply F on both the sides. So I can do this select operation on both sides so that I can reduce the number of tuples, and union is going to be the number of computation which is involved in the union operation is going to be reduced. So that's what is happening here. And same thing, select of F on Cartesian product. So it is select on F on R, okay, first, and then to the Cartesian product if F is pertaining to R. All other cases are very similar to the cases what we have seen in the join operations. So all those things are forced here. These are some of the basic optimizations, okay, which one can think of. Moving further, now let me take an example and explain that how the optimization can be done by making use of those principles. Suppose consider that we are having a two table supplier with the supplier number, supplier S name, and city, and we are having supplier item which is having supplier number, item number, and quantity. Okay. Suppose the query is list names of suppliers, names of all suppliers who supplies item number is equal to I5. Okay. So list name of all suppliers. Okay, should be S here. Now, what are the possible solution? One of the solution is shown here. So I'm do the join operation between S and SI. I'm just taking supplier as S and supplier item as SI for simplicity. Okay, and do the natural join with reference to S number, right? And after that, for the result, I'm applying the select operation where I number is equal to I5. So that's the requirement, right? And then after that, I'm going to do the project operation to select the names. Okay, that is the one. How I can optimize? You can optimize it further by pushing the select operation inside, because you know that I number is holds good only for SI, that is the supply item. So I'm pushing it to inside, right? So I'm reducing the number of tuples here. Then do the join operation as usual. So S join is happening here, same thing. Further, it can be reduced where I'm just going to do the project operation, and that means selecting only those attributes which are relevant. So you know that as per the join is concerned, here I'm concerning the 1 minute. Yeah. So if you look at this expression, there is small correction is required. So what I'm trying to do here is that instead of phi S number, I'm going to phi S number comma S name, that is selecting only the required attributes. And here I'm performing a project operation. Okay. So here there's a project operation with S number and S name. Here the project operation with the S number only. Right. Here we did the select operation. First you do the select operation, and then return the tuple where I number is equal to I5. And outside this, I have to put a project with S number. Okay. Then it will give me only those S number. Okay, and thereby I'm slicing it having only one column, so that I can do this join operation. Here I have to modify this as phi S number S name. That means I'm going to retrieve it out of 3 attributes. So I'm going to get the slicing of this relation having the columns pertaining to S number or the table pertaining to S number and S name. Okay, so that is a further optimization you can think of. It's going to be most optimal solution. What is the reason? I think now you realize the reason for this. So I'm leaving it to you. So the point to be noted here is that we have to perform the union operations as early as possible. That is the first one. Second is do the join operation next. and avoid unnecessary columns during join. Okay. So the point is that if you look at this particular operation, what I said, it's not correct here. So pi, okay, just repeat it. It should be pi s name, pi s number s name, yes, join s number. Then there should be pi s number. Within the bracket, we have select I number is equal to I5, yes I. Okay, then the bracket closes. Right. Now, what typically we are doing here is that we are reducing the size of the table, and note that the number of operations increases. So what is the solution? The solution is that you can perform these operations in parallel. That is the solution here. And the third step says that avoid Cartesian product operations altogether. Try to avoid the Cartesian product because the Cartesian product, the optimization from the Cartesian product is going to be very minimal in this context. Okay, so that's what it says. So these are some of the basic optimizations comes under relation algebraic expressions. Let us move further. Now I'm going to talk about the implementation of some of the basic operations, that is select and join. Okay, for this I'm assuming following definitions. So this means the cardinality of the relation R. That means the number of tuples in the relation R, number of tuples in the relation S. Then there is the number of blocks in the relation R. Ns is the number of blocks in the relation S. Np is the number of buffers used in the memory. I'm going to explain that why this buffer is used. And Ni is the number of blocks in an index file. Okay. So these are the definitions I'm using in my further discussion. Okay. Let me talk about the implementation of some basically two relations algebraic operation, that is the select operation and the project operation. Sorry, select operation and the join operation. And the project operation is very straightforward. You can't do any optimization in that. Okay. Implementation-wise optimization in that. So that's why I'm not considering it here. So select operation. So typically it's a unary operator. You all know. Now, let us consider the expression is of the form select C on R, where C is the condition. So these are the different ways you can execute or you can implement the select operation. One is the linear search, where the idea is that it's the simplest way of retrieving the tuple, where you retrieve each record or tuple in the table and you test the condition, and based on that you retrieve it, and this is the number of block access. Okay, order of NR, where I'm assuming that the number, okay, as I defined earlier, NR is the number of blocks in the relation R. Okay. Now, as for the binary search is concerned, you know that in order to perform the binary search, the table has to be ordered, and it's going to be effective if the condition involves equal, right? Equal sign, or there's equality. So the number of block access is going to be log n with a base 2, and if it is, since it refers to the relation R, so it's NR. The primary indexing. So here we are assuming that the table is ordered on a key field, and condition is also on the key field. This condition is on the key field, then only it will be useful. So here the number of this block access is going to be, since the index file is ordered, so this is a binary search index block. So that's why order of log 2 ni plus data block containing the result. And in most of the cases, it's going to be only one record. So it's going to be +1 in most of the cases, even though the block is not, even though the result is not present, then also you have to access the block. You know the reason behind that. The cluster indexing here. This is possible provided this is effective provided the condition is based on a non-key field, and the table is ordered. The table is ordered based on the non-key field. Okay, so this is the number of disk access. So it's same as the format is same as this one, and along with the primary and the cluster indexing, one can do the secondary indexing also, and the number of block access is similar to that of the primary and cluster indexing. And in the case of secondary indexing, you can have the indexing based on the key field as well as on the non-key field. The methodology is very similar to this, so that's why I didn't put it here. So this is the implementation of select operation. Now moving further, we are talking about the implementation of join operations. Okay, so I'm assuming that R join yes with the condition A theta B, where A belongs to relation R and theta B belongs to relation S, and theta is some condition, right? One of the methods is nested loop method. This is one of the basic method to implement the join operation, and this method is explained here. Here I'm having the relation R. Here I'm having the relation S. The idea here is that for every tuple here, I'm going to check with this tuple, and I'm continuing for all the continuing from beginning to end. Then I'll go for the next tuple, again check, and so on. And that means taking this tuple and then taking this tuple and check for the condition. If the condition matches, then retrieve the tuple. So that's the whole idea. So in that case, what is the number of disk access? Number of disk access is going to be NR, where NR is the number of blocks in the relation R. So that is NR plus for every tuple in the relation R. That's why this multiplied by I have to access that many number of blocks as that of S. That's why that is multiplied by NS. Here I'm assuming that the relation is R is placed in the outer loop. Note that here there are two loops. For every value of R, I'm retrieving this. Second one again retrieving this, and so on. So there are two loops here. So either I'm putting R in the outer loop and S in the inner loop, or I can put S in the outer loop and R in the inner loop. The second case is talks about that. Therefore, I'm going to explain that which one is to be preferred. I'll talk about that a bit later. So these are the two results as per the number of disk access is concerned. This result if you keep R in the outer loop, and this result this gives the number of disk access if you keep S in the outer loop. Right. So this is the nested loop method. Next one, single loop method. Here, in the case of that means there are no two loops. We are going to make use of only one loop. In order to do this one, we have to index one of the table or both the tables. Suppose if you index, suppose index exists with reference to B on S, that means the table S is indexed. In that case, what we are doing is that retrieve each tuple from R, retrieve all matching tuples from S using access structure. That's what we are going to do. So the number of disk access is going to be NR because I have to access all the blocks of this one. And for every tuple, I have to access the index block first. Okay, that's why that is R into log 2 Ni, where I'm assuming that Ni is the index file or the number of blocks in the index file, which is prepared or which is constructed on relation yes. Okay. Similarly, if index exists with reference to A, okay, on R, the same thing, retrieve each tuple from S, retrieve all matching tuples from R using access structure, and hence the number of disk access is going to be this, the same as this. But here NR is NR, it's going to be NS because now I have indexed here. I have an index for the relation R. That's why this is going to be the log is applied to the index file with reference to R. So that's why NS plus S into log 2 Ni. Here I'm assuming that this is the number of blocks of index file which is constructed for the relation R. Or otherwise, what we can do is that you can have index for both R and S. You can have index for both R and S. Okay, that is another way of performing the operation. So we can have both of that. Okay, so this is a single loop method. Moving further, There is another method as far as the join operation is concerned. There is a sort merge join. In this case, the requirement is that both R and S are physically sorted with reference to A and B. Okay. Once it is physically sorted, then the number of disk accesses to perform this operation is NR plus NS, because I'm not going to refer to NR again. That is the number of blocks. I'm not going to refer to a block which is already referred with reference to the relation R as well as with reference to the relation S, and hence the number of blocks to perform this operation is NR plus NS. Right? So this is how this can be implemented using sort merge join. But the requirement here is that the both of the table R and S has to be physically sorted with reference to A and B. That's the requirement. Okay, moving further, I'm going to talk about the use of buffers for performing the join operation. The understanding is the following. Let me jump to this picture first. Let us assume that this is my relation R, which is having this many number of blocks. This is my relation S, which is having this many number of blocks, right? And I'm assuming that there is some buffers are available to keep the sum of the blocks in the memory, right? And that is NB. Now, the notion here is that as per the NB is concerned, one block is reserved for the block of the relation which is going to be placed in the outer loop, and the one block is reserved to keep the result which is generated for the join operation, right? And so that's why the effective the remaining blocks, that is NB minus 2, is used to fill the blocks of the inner loop, blocks of the relation which is used in the inner loop. In that case, the number of disk access is going to be NR plus NR divided by NB minus 2 into NS. Okay, here you are taking the relation R in the outer loop and relation S in the inner loop, or it is going to be NS plus NS by NB minus 2 into NR. Here we are keeping the S in the outer loop and R in the inner loop. I'll just take an example to get an idea. Suppose you take this example here. I'm having the relation R is having 3 blocks, 1, 2, 3. Relation S is having 2 blocks, okay? And NB, I'm assuming that NB is having 3 buffers, right? So one buffer is used to keep the block of the relation which is outside. In this, one is going to be the result, and in this example, we are left with only one block. Okay, that's what is happening in this example. Now, if you keep R in the outer loop, so I'm keeping this in the outer loop, so this is going to move here. So there's a one block access, and this will be reserved for the join of that block as well as the block which is corresponding to yes. So this can't be touched. So I'm left with only one block. So I'm going to move this to here. So that's why one access, and after that, I just move this to here and do the join operation. That's another access. So there is that's why whenever I'm having the first block here, then there are 2 disk accesses that is corresponding to yes. Then the second block here, there are two disk accesses corresponding to here, and the third block access, there are 2 disk accesses corresponding to this. So the total number of disk accesses is going to be 9. So if you apply that to this formula, you are going to get the number of 9 disk accesses. Now assume that you keep S outside and R inside. In that case, I'm keeping S here and I'm bringing this block one by one into the NB. That's what is happening. So yes in the outer, yes, this is the first block, and then this is out. This is for the result. So for this buffer, I'm going to bring the relation block, the relation R block here. So first time, second one, third one. So 3 blocks, 3 times, and then I'm keeping this one here. Then 1, 2, 3. So it's going to be 8 accesses. Of course, one can always argue that if I'm already having the if I'm already having the block, then I can start from that block itself. But there are also some of the optimization you can think of. I'm not considering that optimization. My point to be noted here is that if you keep R outside, there are 9 disk block accesses. If you keep S outside, there are 8 disk block accesses. So the moral here is that keep the table which is having less number of blocks in the outer loop. That is advantageous, and the number of disk block access is going to be reduced. So that's how the optimization one can do. But if the number of if you are provided with the buffers. Okay. So this is basically some of the basics regarding the query processing in the centralized environment. Definitely, this is also part of a distributed database management system query processing, and we are going to talk about the details which is more specific to a distributed environment. That we are going to start from the next session. Thank you.